Okay, so welcome back. We're on track of learning how to use existing tools, existing libraries to do common scientific computing tasks. And so in that vein today, we are going to look at root finding and optimization. So those are two topics, but are kind of similar, as you'll see. We'll start with root finding. It turns out it is quite common to want to solve an equation numerically when you're doing scientific computing. And a lot of equations can be cast in the seemingly simple form of some function acting on the variable x that we want to know to be 0. So if you have such a shape of your equation, and where f is just a simple function, not a differential form or anything like that, if x satisfies this equation, we will call it a root. I don't know if anybody still knows why it was a root, but it's a root. Now, this deceptively simple form can stand for a set of equations. You could think of x as being a vector and f being a vector of functions. And so the general case would be that you have n functions of m variables, all of which have to be satisfied to be 0. And once it's in that form, you can see a lot of cases can be formulated in this way. In fact, if you have no differential equations, no differential operators in there, no difference operators in there, basically it'll be of this form, and you can always make the right hand side 0 by the appropriate transformations. Now, while this is the general case, it'll turn out that the one-dimensional case, which we could say is this one, is a lot easier to solve numerically. And I'll explain why. So we'll do that first, and then we'll hopefully be able to build upon that to get the general case done. So I plotted a function here. Wow, that became big here. Okay, here's a function. The dotted line, which luckily doesn't coincide with the line of the screen, is where it's 0. And but it does seem that the root is pretty much right on top of here. That's funny. So we have our purple curve, or pink, depending on your taste. And somewhere it hits the x-axis, and that's what we want to know. So we assume that we have the functional form of f, and we want to know where it crosses the x-axis. Now, the first thing you would want to know to do this numerically, because we've plotted it and we can see where it is, so we are done, right? The idea is that there might be cases where just plotting it would be too expensive, and we want a more clever way to find this root. So imagine that I was only allowed to, say, evaluate 2 points at a function. It's that expensive. Then I couldn't get the whole curve. But what I might be able to get with this 2 intervals, or 2 points, is I could get lucky and get and evaluate a function at point A, let's say that's -4, and point B, let's say that's 3. And what I would notice is that the function is negative at -4 and positive at 3, which means that if I happen to know that this is a continuous function, there must be a root in between A and B. So the first thing to do, if you don't know anything about your function, if you want to have any hope of finding a root, is to bound that root. Find an interval where the function is negative on one side and positive on the other side, or the other way around, because that way you know there is a root. And so that's going to be always the first step in any numerical procedure, finding this. Now, what's nice about one dimensions is that once you have those 2 points, you know that somewhere in between there's a root. This isn't necessarily true, or not that easily true for multiple dimensions. I could have a positive and negative value, but the root could be all the way out there. They're not linearly in between there. So by subsequently refining this interval A and B, I will zoom into the root. I'm sort of guaranteed to find a root. And that's why 1D is the one-dimensional root finding is so much easier. You're guaranteed to find a root. So how do we find this initial bounding interval? It's a bit of an art. You kind of have to know a little bit about your function. So often, if you can, you will plot the function. Or you would plot a function that's kind of like it. If it's very expensive, you could make an approximation to get an idea of what it looks like. But if that's not feasible at all, you could make some conservative guess. You could say, well, the sun is somewhere between here and and a parsec, somewhere in between, very safe bounds on where this route would be. You could do that and then start, or you could even be more sort of shoot from the hip and just try something. Say, well, it's going to be somewhere there, and then if it's not even close to it, you sort of expand. So there's ways to figure this out, but you kind of have to know the order of magnitude of your variables. Where should you look to find this? There's no fixed numerical routine that can give you that, because it would have to know way too much about your function. Okay, so you're going to try and find this interval one way or another, based on it. Now, even so, some cases are really hard to detect, and it's very hard to find these bounding intervals in those cases. I picked 3 here. Here's a root that happens to be also a minimum. And when that happens, there is actually no sign change. And you will not find this root. Even if you found this root, you couldn't really be that sure that it is a root. Who says that because if I'm finding this numerically, who says by numerical round off, this one is actually supposed to be just on top or just below? Essentially, this likely just falls below your numerical radar, unless you know that something like that exists, and then you will have to say, well, you know what? I know it exists. I'm going to look for the minima. Now I'm going to look around that minimum and see if it's within a tolerance of 0. In other words, this troublemaker here needs some special care for you to find it. Sometimes it's just easy to miss a root. So you could mention that here are some roots, but the interval where it changes sign is very small. So if I just tried it and I just picked a point A on this side and B on this side, I would never guess that there is a root. Right? I'd have to. So although once I have bounded my interval, I will find a root, it's not even guaranteed, not very easy to find that interval in this case. And of course, if my function isn't continuous, that's the third case. If there's a singularity, say, an asymptote, then I could have a change of sign, but it doesn't mean there's a root. That just means that the assumption that I made about the function being continuous is wrong. So in that case, what you would find, I guess, is the singularity rather than the root. So let's suppose that we don't have one of those difficult situations, so we've properly bounded a root. What's next? So there's a couple of sort of standard root finding algorithms out there, and we'll look at two of them in details. The others are more or less variants of it. There's bisection, the false position method, Brent method, NewtonRaphson. All of these do the same thing. You take an interval and you try to make that interval smaller and smaller, or you try to zoom into the root. The difference is in how they do it, and how they do it also determines how quickly they converge, which means how many steps do I have to take to be within a certain given tolerance close to the root. And since we are assuming that evaluating these functions is costly, the fewer steps I have to take, the fewer times I have to see what is the value of the function in my new interval a and b, or on the borders, the quicker it is. So fast convergence is good in these cases. There could be stability issues. There could be some of these require you to know the derivative of your function f. NewtonRaphson is one of them, and so we'll see that. These are all fairly general one-dimensional root finding algorithms. If you have a polynomial, don't use them. There are special ways of getting the roots of polynomials. If you have eigenvalue problems, we've looked at an eigenvalue problem, you're looking at it now in the problem set. if you've taken linear algebra classes, which I'm sure you all have, then you know that you can write an eigenvalue equation, which is a polynomial equation in the eigenvalue. And so it says, I don't know, lambda to some power plus lambda to some other power blah, blah, equals 0. That's an equation of this kind, and you would think that you would just use these root finding solutions to find them. Not a good idea. And it's kind of unstable, and there's way better ways, such as using layback. There are cases where you don't use these, but for generic functions, you can use these guys. So let's look at one of the simplest and easiest to understand methods of finding roots, the bisection method. Here's our same function a and b. We're going to change the interval, so this is a1 and b1. We're going to change a and b to get closer to the root. And what we'll do is we'll find the midpoint. So basically the average of a1 and b1, and we'll check what the function value is at that point. And in particular, we want to know what its sign is. So here we've noticed that the sign of the midpoint, of the function at the midpoint, is still positive. And if it's still positive, it becomes the new b. That way, my new interval a1, b2 still brackets a root, still is a bound on the root. And it's a smaller interval. So doing this successively, finding another midpoint, in this case the midpoint has a function value that's negative, it becomes the new a. So now my new interval is a2, b2. And you just continue like that. So you get a finer and finer bound on the root, which is kind of nice because you automatically sort of get the error in your solution. So you could say the next midpoint is your best guess for the root, and your estimate for the error is the difference between b3 and a3. And you'll continue until that interval is small enough for you to accept this as a reasonable, accurate solution. Does that make sense? Okay. So that's one way. It's not very fast, but it is very easy. You could write that one yourself quite easily, but you won't. And another sort of improvement on this is what's called the false position method. What that does, it starts the same way, but then rather than finding just a midpoint, which is kind of arbitrary and doesn't really have anything to do with the function, we're going to use the function values themselves to come up with a better point as our next guess by making a linear approximation to the function. So if we make a linear approximation, obviously we've used the values of fa1 and fb1 here. We can see, okay, this linear function, I can evaluate when it hits 0. It's just solving a simple 1D linear equation. I don't need to evaluate functions for it. It gives me an estimate of where I should put my next x. So rather than taking the midpoint, I find an x that solves the linearized equation. And then I do the same thing. I figure out what the function value there is. I see if it's positive or negative. If it's positive, it becomes the new b. And then I continue. So I've got a new interval. I'll take another linear approximation. I'll find where it crosses the x-axis, and I will see what happens there. In this case, it becomes a new a. Now, as you're zooming in, if your function is smooth, this linear approximation will become better and better, assuming that the second derivatives are bounded. And so this tends to be faster than the first method. You're using some of the function values, that information that you had anyway. So this is per step just as expensive as the other one, but you'll need less steps. That's it. Here's a few other ones that you should know the names of if you're looking at the second method is very similar to false position. Ritter's method, rather than doing a linear fit, does an exponential fit, which sometimes helps. There's different fit. You can use quadratic fits rather than linear fits. You could see how this could be expanded. Quite a different kind of root finding is one where you can use the derivative. So rather than saying I have 2 points and I take a linear approximation based on those 2 points, in NewtonRaphson, you take one point, x, you figure out what the derivative is at that point. So this requires you to know analytically what the derivative is of that function f. And then you basically just follow the tangent and see where it hits the x-axis for your next point, x2. From there, you'll do the same thing. You go, okay, what is the function value there? What is the derivative? If I follow the tangent, where do I cross the x-axis? And you repeat. This has a very fast convergence. Once you're near a root, this is basically done in no time. So, sorry. So is that clear? So you're using again more information, right? You're using the point and its derivative. So those are two function evaluations. So it's a little bit more expensive, depending on how expensive the evaluation is of the derivative. And if you don't have the derivative, you don't have this. But just to sort of show the difference between the different solvers, the bisection, for each of them I've here listed the convergence and the stability, by which I mean what is the next error based on the previous error. And in the bisection method, you could see the error as being the distance between the two endpoints of the interval. For the NewtonRaphson, you could say it's the distance to the real root, which of course we don't know, but that's okay. So in bisection, not surprisingly, on average, exactly, the error is half the error before, because the interval is cut in half literally every time. So that is sort of a linear scaling. Turns out that this false position has sometimes it goes as 1/2. But there's another part that goes a little faster, and then C kind of depends, I think, on the function, so it's not so clear, but it tends to be a little faster. And NewtonRaphson basically goes quadratically. The new error is quadratically in the previous error, which means that if I were within, say, 10% of the root in step 1, I'm within 1% in the next step. And it just goes very, very quickly. But there is a price to be paid in terms of stability. So what can happen in NewtonRaphson is that if you're in an unlucky point, so let's go back to suppose I started over here as my initial guess. Rather than my answer ending up closer to the root, the tangent would take me all the way out of the screen. And it'll take a while for it to find its way back. And it's not even guaranteed. It could actually never find its way back, because who knows what the derivative is there. So it can be unstable, used on its own, but it's very fast. So what typically happens in sort of canned solutions is that people take a few steps of bisection or false position or any of the other ones, and then they refine their root at the end by doing a couple of NewtonRaphson iterations. So once you're close to your root and the function is more or less linear there, it's a good way to sort of get all of the precision you might get. Mm-hmm. Yeah, so all of these are asymptotic. So they're only really true if you're already quite close to the error. So C is never like it. Yeah, it's an asymptotic argument.
And the Ritter's method, 2 steps ahead.
Yeah, so this is it works kind of funnily. It kind of takes 2 steps, but then in those 2 steps you get a square. So anyway. Yeah. Now, you don't have to program these things in yourself, and you probably shouldn't. You can just use a library, and in this case, the GSL has that. We saw the GSL before already, so I just put out a list of other things it can do. So it can do root finding, it can do minimization, which we'll look at in a second. Do sorting, integration, ODEs, we saw that, Monte Carlo integration, polynomials, special functions, vectors, matrices. And so we're going to use that here too. And here's a little example of the solution to the problem that we just saw. So this is actually the function that we've been seeing. This was our purple curve. with very specific values of the parameters. So there's, it is really just meant to be complicated for its own sake, and yet have only one root so that we can know that we're doing things right. So I just made this up. A, V, W, B, C are just some parameters. And so I want to point out a few things here because you're going to be using something like this in the assignment for next week, due for next week. So you need to specify the function. In this case, I've called the function example function, which you can see computes this thing, but in a kind of funny way, because it needs these parameters also passed in. And because this is a C library, it can only pass them in as a void pointer, meaning it has given up knowing what it points at. Okay, that's what a void star, a void pointer is. So the first step in the function is to say, well, you know what? What this param really points at is a structure that has 5 doubles in it. That's called a params. And so once I've sort of told the compiler, think of this as a params, as a set of 5 parameters. Since it's a pointer, I can get A out of P by doing this P point to A combination. So you have to read this this arrow here as a very tight combination. A is the A parameters that is stored in P, V, W, B, C. And once you sort of look at it that way, I hope you see that you have this function again. And then the way that the GSL wants you to solve this is it wants you to allocate a solver. So there's some sort of structure called GSL root solver that you allocate. And in this case, I've chosen the Brent method, but I could have chosen any of the other ones. And so you've created now a solver. This is sort of an object-oriented way of doing things without using actual objects in C++. So everything is hidden in this solver object. Then I have to pass the function into a wrapper. There's a wrapper because I have to pass both the function and its parameters, and so this wrapper thing has a functions component and a params component that is set here. And then I pass that to the solver. That only initiates it. So I say, okay, we're going to solve this. Here's the function to solve. Here are its parameters that I need. And then just hold on, and I'll tell you what to do next. And what we'll do next is take these iterations, take these steps. And in each step, we will iterate the solver. It does one step to get closer to it. And then I'll ask the solver, okay, what is your current best estimate for the root? What is your current lower bound, your current upper bound? And then there's a function to test whether that interval is small enough. So that's what this test does here. It tests whether the interval between low and high is smaller than 10 to the minus 3. If that is so, it will set status, and that's what this status thing is doing here. If the test is successful, it will if it's successful, then it will set the status to something that causes the iterations to stop. So if I did, so this is the code, and all of these codes kind of look like this. So at some point you'll have to look at that a bit more. And then we want to compile it. And so if I'm pretending to be on Cynet on the GPC here, I load the GCC module and the GSL module, and then I compile my little example. Say it's called x.cc, and because we're on Cynet and the GSL is not stored in a standard library, I have to give it the -i and then the Cynet GSL inc environment variable that points to where the header files are. And with the linking, I'll have to do something similar. I have to say where these libraries are by passing the library path. If you're on your own machine and things are standard locations, if you've done that, don't give it a -i or a -l. It'll just throw things off, and these environment variables won't be there. But this is how you would compile it. And here are the libraries, the GSL, and the GSL needs CBLAS for it to link. And then the output is kind of trivial. We have, in this case, only 3 iterations. There's a lower and upper bound. You can see the Brent method is pretty fast, because in 3 iterations, apparently gets within 10 to the minus 3. And here's our root. I didn't have any access stick, so you can't see if it's right, but it's right. And the error is indeed 10 to the minus 3. Okay? So I didn't have to program anything in. I could use a fancier method like Brent, which I didn't explain to you, but it has some nicer properties, and just use it. So that's one-dimensional. Multidimensional, so where x and f are vectors, or if I write it out, a set of equations, is harder. It's harder because I can't take a finite number of points, a finite number of evaluations of these f's, and bracket the root or surround the root. Right? With points in more than one dimension, I can't surround anything. Right? I would need a surface, but I would need an infinite number of evaluations of f to find that surface. Can't do that. Another way to think of it is to say that each of these equations themselves defines a d-1 a hypersurface, and then I need the intersection of d of these. Again, that's a tough problem. So pretty much the only surviving candidate of solving these equations is the unfortunately unstable NewtonRaphson method. It generalizes to higher dimension because it didn't do this bracketing. It took a point and then it took the derivative and it gets closer to the root. And that we can do still. So here's sort of how you do it in higher dimensions. You have some guess of x naught. You want to know, well, but it's not right. f x naught is not 0. How do I get to 0? Well, I just assume that my next step is going to be small. I do a Taylor expansion, and I will find that the step I have to take, this delta x, has to satisfy f equals minus j. J is a matrix times dx. J is the derivative matrix, so I have d dimensions, then I have a d by d matrix, and that's what you get. So formally, you would have to invert that matrix and to find where the next step goes. So you figure out the derivative matrix, the Jacobian, and its inverse. You apply it to the function, which is a vector. You get a vector back. That is the step that you should take. Okay. Now, I hope that you remember from the linear algebra lectures that you should never take the inverse. If this is 2 or 3 dimensions, maybe an inverse is actually not so bad. But in general, what you're solving is a linear equation here. This is ax equals b, just slightly rearranged. So solve that linear equation, you find your dx, and this can be done. But of course, we have some instabilities to worry about. We could be shot way out of the area of the region of interest, and so there's almost always an extra to this. The simplest way you could do is say, okay, suppose that that it tries to shoot me all the way off. Well, I won't if that makes my function bigger in absolute value, and I'll do something else, something that gets me a little closer. Maybe I don't take it all the way to the edge, and so by making these sort of extra safeguards, usually you can find your root. There's, however, no longer any guarantee. Okay, yeah.
See, back choosing their initial violator is.
It essentially does that, but it still tries to use that point to know what the next guess is. So it probably takes a step into that direction, but not all the way to the supposed root. There are other ways to do things where you try to pretend like you are bracketing a root, but anyway, so that's. But yeah, essentially you're kind of trying again. So that's going to be. So that's the multidimensional case, which is obviously more general, and it'll probably be your homework. The same thing can be done with the GSL. That's supposed to be bullet point also in the GSL. So again, you don't have to do this yourself. Sometimes you do, especially if you have to make sure that this linear step is done properly. The calculation of your J might be something that is in your code, but a lot of cases you can use the GSL to drive this root finding. Okay? So kind of related to root finding is optimization. Optimization is when you have a function of, say, d variables, and let's say it's just a single valued function f, not a vector, and you want to know for which x it is at its minimum. And now minimization is the same as maximization of minus f, so optimization is the same as minimization, maximization. So I'm going to talk usually about minimizing, finding a minimum, but no, it's all the same, right? Now, we could cop out and say, well, the minimum of this is where the derivative with respect of each of these variables is 0, so we'll just do df dxi equals 0. That gives us a set of d equations for d variables, and we put it into our root finding solution and done. Turns out that that is not a particularly good way to do it, or it's definitely not the best way to do it. Again, as with many of these cases, if you just have a few variables, you might get away with it. But what turns out to be the case is that you want, there's something special about these equations, right? They are all the derivative of one function f. And whenever there's something special, there might be a better way to do things. So optimization is something where this is the case. Again, the one-dimensional case is substantially easier than higher dimensional cases. And just as with roots, although I didn't point it out, there's no guarantee that we'll find the global minimum. This is true for all of the numerical methods that try to minimize things. Your function might have several minima, by which I mean places where the tangent is 0, is horizontal. It might even be a good routine and find several of them, but there's no guarantee that we'll have found all of them. There's basically too many ways that could be minima. You could have an infinite number of minima if your function is odd and strange enough. There's no guarantee. So here's a function with, as I've plotted it, 3 minima. And let's look how you would minimize that in one dimension. So we see some local minima. This guy, and this is going to be the global minimum. We would like to find this one, but to be sure that you find that one, essentially you have to know a little bit about your function. So let's assume we don't. Let's not assume anything, but let's try and come up with a way to at least find one of them. And it's going to be kind of a generalization of this bracketing idea in root finding. But this time we are going to use 3 points, A, B, and C. And rather than having a sign change, we're going to have them sort of have a direction change. Going from A to B should go down, and from B to C should go up. It's kind of a sign change of the derivative, except we're not using derivatives, so we're just using the function value. Okay. Now, once we have such a bracket, and that means we have to find 3 points in this case that find this bracket, and how to find it again means knowing a little bit about your function and kind of trying. Once you have this, there's ways to refine A, B, and C, such that A and C get closer and closer together. 2 sort of standard ways are the golden section and the Benz method. We'll look at golden section for a second. So same kind of strategy. And again, this works in one dimension because I can take basically 2 points, a finite number of evaluation of the functions, and be sure that there is a minimum here. If this is a smooth function, once I have this, I know between A and C there is a minimum. Okay. So I'll look at the golden section method. So here's the idea. We have 2 intervals essentially from A to B and from B to C, and we want to find a new point in either one of those 2 subintervals, new point D, and it shouldn't coincide with B, it should be somewhere in between, and we'll try and see if we can push these boundaries closer together. Okay. We need a prescription on how to find a new point. We don't really want to do a midpoint, we want something that sort of works optimally, and it turns out that if you take your point D to be a fraction W into whatever is the larger of the 2 intervals, that works if you take W to be the golden section. And so, okay, we'll believe that. Let me show you how this would go. So here I put 3 dots on this curve that are bracketing a minimum. Here's A, here's B, here's C. the value at B is lower than at A and at C, and so this brackets 1. So what's going to happen in this routine and this algorithm is we're going to take the bigger of the two intervals. So these ones are the furthest apart, so that's the bigger of the two intervals. This other interval is smaller. And I'm going to go a fraction w away from the midpoint into that interval. That takes me there. So here's my new point, and I'm just going to see which of these 4 points, if I take 3 in succession, bracket another minimum. This one does not, because I keep going down. This one goes down and up, and so I take these 3 as my next set of points. I'll do the same thing. I'm going to look which of these intervals is the largest, and I'm going to go a fraction w away from the midpoint in it. That turns out that this is the largest interval, and so the new point is here. And I can do the same thing. I can see, okay, which of these form a bracketing? Well, this does not, and this goes down and up, so this here again has a minimum. So you can see that each time, once I have this bracket, somewhere in between A and C, there is a minimum. Right, somewhere. I started out in a case where I had both minima in here. So it wasn't quite clear which of the two it was going to find, and we end up being lucky here, and we're going to find the true global minimum, but this was very sensitive on our initial guesses. Where am I? So the next point I'm finding is that is this guy, and again I have some bracketing. Something happened. Another bracketing gets me to these 3 points. Yet another one gets me to these 3 points. So you can see you get closer and closer to the actual minimum. Make sense? So it's the same kind of idea, but with 3 points. And as long as you have a reasonable strategy, a reasonable algorithm, you'll find this point. Now, I keep stressing this, but it's important to know there's no reason we would find this minimum. I am pretty sure if this initial point was chosen a little bit further here, or this midpoint maybe closer to the local minimum, that's what we would have found. So the only way to know this is to try. Okay. This is, by the way, one of the reasons why when you do have an eigenvalue equation or another polynomial equation, you use specialized routines, because for polynomial equations of degree n, you know there are at most n roots. You could find ways to solve it. With eigenvalue equations, if you have a symmetric matrix, you know you have n roots if it's an n by n matrix. So you know more about it. That's why you don't want to use these kind of things. And the same is with minimization. Now there is a way to help you out here a little bit, using random numbers and local minima. We're going to look at that more later, but first let's look at multidimensional minimization. So we're again in trouble here. We can't come up with a finite number of points and figure out that somewhere between those points is a true minimum. But it's not as bad as for the root finding. See, with root finding, I could try and, so with root finding, the idea is, okay, I have a change of sign, and I'm going to try and get closer. But with multidimensionals, being closer to 0 doesn't really mean that you're closer to the root, because it could just veer off of 0 again and go away. So the nice thing about minimization in a sort of informal argument is that as long as you keep going down, you're closer to the minimum. And even if you aren't, if what you want is the minimum value of that function, well, you at least get a better upper bound to that minimum each time you go down. So going down is actually easier than just finding a root. Now, most of these methods are built upon one-dimensional methods, and they will try something like a trial point. It looks a little bit like NewtonRaphson, but it doesn't necessarily need to use the derivatives. You could, of course, but that's not a common case. So suppose you have some trial point P. You can imagine trying to find a minimum by going in one direction and saying, okay, let me try and find the smallest value of the function in that direction. Then going in another direction, can I go down a little bit more? Can I go down a little bit more? And then you hope for the best. I mean, you test for convergence. So this is the simplest and workable way of going about doing this. It's just not very fast. Suppose I had this function. These are the contour levels. The minimum is actually somewhere here, and I start my initial point P over here, and I decide to first try and find the minimum in this direction, basically in a section of the space, and it turns out that this is where my minimum is. And from then I'm going, okay, that was the x direction. Let me try if I can go to a lower point in the y direction. That turns out to be this guy. I do this again. So eventually I will converge, in this case, to this point. Obviously, there could be multiple minima, and I could find the wrong one, but this is how this would work. But you need a lot of steps. And you could kind of see that you probably get a lot better if this thing was a little bit tilted, so that the direction of my initial try is sort of aligned with going into the direction of the point. So all the more clever ways will try to do that. We'll try to figure out, okay, what is the best direction to try? Because I don't have to go just in the x or the y direction. I could go along some other line. So there's kind of two ways to do this. But they all use this idea of finding directions that are good. So one is steepest descent, and that kind of sounds like, especially if you know the derivative of a function, this could be very good. So suppose we knew the derivative of this function, it will point in like orthogonal to these lines. So you'll find something that kind of points this way, which probably means that our first step would get us somewhere here. And if we kept doing that, that sounds like a good idea. Find the direction in which the function changes the most and go down in that direction. Okay, that's steepest descent. Turns out that if you do that, you're still going to make a lot of these turns. And so one of the reasons that happens is that you take your steepest descent, and so you're already in a very sort of local, or one-dimensional minimum. The next step, you're going to naturally go away from that, right? So, which might mean that you actually move a little bit away from this routine, because you're choosing, okay, I need to go in a different direction. So you kind of have to make sure that each of the subsequent directions that you take aren't undoing the work you did in the previous step. So this is the danger of just doing steepest descent. You take a step in a certain direction that you think is the best, but it isn't quite the best. The best direction would be this, right? We're going to go somewhere around here. And so now I'm taking a turn without really taking into account that my previous step, that I'm going back a little bit for the previous step. So there's a way around that, a way to do that in a more consistent way, by using what's called conjugate gradients. And the conjugate here is kind of a fancy way of saying the subsequent steps are not undoing the work of previous steps. And so you need some properties between the subsequent directions for that to happen. And that's all I'll say about this, because I don't want to get into it too much. But it works better, and especially it's basically solving the whole system as if it's quadratic. So this little picture, this is not a quadratic because they're not ellipses. There's some anharmonicity in here. But if it was, if it was a quadratic equation, then the conjugate gradient one basically solves the whole equation in one step. It figures out where's my steepest, where's my direction that I should go in. It goes in that direction, and that's it. And so the closer you get to a minimum, the more it will look like a quadratic function, and so the better it will go without having to do all these little steps. So this is going to be typically your method of choice. Again, these are in the GSL library, so if you're doing minimization in multi-dimensions, use a library. Don't try and outsmart these algorithms. Yeah. No, so you just need a first derivative to do. So you only have to know kind of what direction so yeah, what direction locally we have to go into.
Oh, I don't need the 6%.
No, so so it uses the same information, but it just makes sure that you don't do the same thing or undo the same thing again. That's yeah.
How long? Where do you stop for the next step?
Right. And so that's you could go you typically go to where it's minimum. But you make sure but you use that in the next step to make sure that the direction goes. Okay. So in this case you go all the way. There are alternatives where you could go, no, let's just not go all the way. Let's go, because you can imagine that it might be a good idea to take smaller steps. And that can have merit, especially if you're far from the minimum, that will have merit, but I think the standard thing is just take the whole step. Okay, so we can find minimum. Again, it's not guaranteed you find it, and it's not guaranteed that you will find the global one. So if we want to find global minima, we are going to need some help. And so this is one way of getting the help. We're getting the help from getting some inspiration from nature. Nature is a ridiculously good minimizer. Here's some ice crystals that show that it is a ridiculously good minimizer. The lowest energy state of water molecules in ice are a very particular arrangement of their molecules. And by chance, you're not going to find this. But somehow, nature, when you take the temperature below freezing, very easily finds this. Not always easy, but very easy find this, and it freezes. How does it do that? Now, I'm going to answer that question really, but the way you could think about it, and the one that will help us find minima here too, is that while we have our temperature dropping, we don't just have one configuration, right? One of these molecules. They're moving about. They're jittering. They're exploring all possible combinations, and they do that because they are moving around, because they are exploring these things. One of these is going to be of lower energy, and as you keep decreasing the temperature, they will kind of get stuck. So let me show you what I mean by that. So suppose that this is the functional form of the energy landscape of ice, which it is not. But let's suppose that there's a typical energy scale associated with each temperature. There is. And so if that's high enough, essentially what I can do, what can happen in nature while it is at a temperature, is that it can explore all of the possible configurations. So think of the x-axis as a configuration space and f as energy. It just moves around fairly easily. It doesn't really even see. It's like it's on the top of the sea, and it's very deep. There's some bumps here. It doesn't care about that. But as I lower the temperature, it's like lowering the level of the sea or of the lake. I suddenly start noticing these bumps. So now it will be harder for my configurations to go from here to there, but they'll still figure it out. They won't feel these things yet. But if I keep going down, eventually the only configurations that I can explore are the ones in the actual minimum. I have to do this carefully because you can see the potential of getting stuck here, right? So while I'm moving it, I have to have some sort of possibility of jumping from one to the other. So here's where the art comes in. But if I manage to do that, if I manage to explore the space, and we'll see how we can do that with random numbers next week, I have a way better chance of finding the actual minimum than by just trying these minimization routines. And this is especially true if I have many minima. Where none of these are, you only find one minimum, right? In this case, you could actually see, suppose you stopped at this point, you could actually see a bunch of them are here and a bunch of them are here. you could do the probability distribution, and you could see, okay, I'm finding 2 minima, right? So you actually find more than one at the same time. So I'll leave that till next week to see how we could implement it. It is in the GSL. We need random numbers, which we're going to do next week anyway. But this is one way, a slow way. It converges slower than the other ones. It's non-deterministic. It's slower, but you have a better chance to find the absolute minimum. So that's simulated annealing. You pretend like you're lowering the temperature of your system. Okay. I think that was it. So you have one more day for the current assignments. We'll leave you at that. And then tomorrow, I guess we'll post. Well, we might get to posting the next one today, but it will be due a week from tomorrow, because you should have a whole week. Okay. All right.